Morning.
Good morning. Okay, now the microphone is here.
It's his birthday today. Ori, don't you do that anymore.
His mic helps you pull your ears up. So you grow bigger.
All right, thank you.
How do you get the screens down? I think I've got to switch the system off and switch it on again. Because the screen will come down. Oh, I can possibly use the boards, but I didn't bring the markers.
Can I check the microphone? I didn't get any radio from it.
No, I haven't started yet because I can't get the screens down. So I'm just kind of talking to you, but talking to myself pretty much. I'm switching off the whole system and then start again to get the screens down.
Oh, no wonder.
Because they're not coming down. Sorry. I will get the microphone. Okay, apologies about the delay. You know, the usual. The engineering method never fails. Switch the thing off, switch it on, so it works. Thanks for coming in such a large number. Well, this is more than what I expected. After the wild parties you had last night, I guess. Anyway, so we have a negative feedback loop system. So we can identify 4 different signals here, X, Y, Z, and W. Which one is the one we call error, the error of the system, the error signal? No idea. X. Well, this is an error. X is not an error. Okay. Or you know nothing about the errors. Okay, you made no errors last night, okay? At least those who were here, I assume. No. Yeah. Why is the error? Y is the error. Why is Y the error? Why do we call this error? Because this is effectively the difference between the input and the output. And knowing that when we apply an input, we apply an input because we want to achieve a certain output. So we don't just apply an input for no reason. Sometimes we do that. But the idea is that the input corresponds to the, what you want the output to be. So you apply an input hoping to achieve a certain output. If you don't, then you have error as a difference between the input and the output. Okay. You apply an input, you get an output. Output is measured through this sensor, through this feedback loop, and compared with the input. Now, if that comparison gives you 0, you have no error. So you achieved what you wanted. Okay. Once again, temperature control system. When we start the air conditioning, we hope to achieve 20 degrees. Okay. If that's what we have, this plant, this system here, the air conditioning system, will work in a steady state regime, maintaining 20 degrees. If there is a difference, you know, if someone opens the door, so as a result of that, we have a difference, this error signal will drive the air conditioning up or down to increase or decrease the temperature here. Okay. Cruise control, again, with the car, if you set it to be 60, if there is any deviation from 60, this sensor will tell us that. Compare the actual speed with the desired speed, and this error signal will drive the engine. Increase RPM, decrease RPM. Okay. Now, so we would like to have this error 0. Okay. But it's never the case. You always have certain transient processes until, in the steady state case, you will ideally have a 0. Okay. And that is what the lecture 10 is about. It is about steady state errors. So do we always have a steady state error equal to 0? Does this negative feedback loop guarantee that the output will be exactly what we want? Okay. So let's talk a little bit about errors first. So this is an open loop system where you simply apply an input expecting, hoping, praying, hoping that the output will be what you want it to be. Or you have a closed loop system where you're trying to bring this error to 0. Okay. So what is the error when you have an open loop system? Well, it is simply the difference between the input and the output, R minus C. So this case, well, you can rewrite, instead of C, you can write R times G, so it's R minus GR. So the open loop, EO, open loop's error is R times 1 minus G, where G is the transfer function. Now, this case resembles someone who is just starting to drive. So you are pressing the accelerator pedal, hoping to achieve certain speed, but you have no idea what your input will result in, what kind of speed you're going to get. So, but, well, it's not exactly a good example. So our beginner driver is also an excellent engineer. Now, can you imagine that? I guess you can see yourself there in that role. So we know our beginner knows the transfer function of the car. So he or she knows what kind of input to apply to achieve the output, desired output. But what happens is that there are so many factors that make this G a little bit uncertain. You know, is the cross-section of the nozzle really properly estimated? Is the quality of the fuel right? Or how about the temperature affecting the performance of the engine? So there are all sorts of things that we can't predict, and that will result in a different output for the same input, depending on, as I said, on so many circumstances we can't really predict. State of the tires, you know, so there are so many, or the road itself. Okay, so this is an open loop error. It is open to to any deviations in terms of the parameters of what we think is constant in the transfer function, and also open to influences of all disturbances that may affect our system. In a closed loop system, the closed loop error is here, as we just agreed a few minutes ago. So closed loop error equals R minus this signal here, which is CH, R minus CH. On the other hand, C equals EC times G. So we have G, EC, H. So we have EC here and EC over here. So EC, closed loop error, equals R over 1 plus GH. So these are the two errors, open loop and closed loop errors. We said we can't avoid transient processes. So during the transient processes, there will be errors. But how about the steady state? When the transients are gone, all equal to 0, what happens? So the steady state error in the open loop case is S times E O of S. Same goes with the closed loop error. Limit when S goes to infinity, S times EC of S. Let's assume unit step input for simplicity. Okay, so in this case, R would be 1 on S. So we have S times 1 over S minus G over S. That is equal to 1 minus G naught, G of 0, 1 minus G of 0. For a closed loop case, again, S times R is 1 over S over 1 plus GH. So that will give us G of 0 and H of 0 down here. G of 0, if you remember, is the steady state gain, or DC gain. So when S equals to 0, we end up with a DC gain. Okay. DC gain, when you have a plant, so whether you have a compressor in the air conditioning, whether you have a car engine or whatever, DC gain is normally greater than 1, much greater than 1. So if you have an energy source DC gain will be huge in your system. So let's assume for this analysis it is simply greater than 1. G of 0 is greater than 1. Now that means, sorry, here, that that's okay? Okay, oh, okay, maybe I touched something.
There we go.
Okay, sorry. Okay, maybe yeah. I'm wearing so many gadgets. Okay, fortunately enough pockets here. Okay, so if G of 0 is greater than 1, if the steady state gain is greater than 1, then this term here can be just anything. Can be any value imaginable. If we also assume h of 0 is usually close to 1, it is just a sensor, doesn't give you any amplification or any attenuation, so it is roughly 1, so it is close to 1. So in this case, if we assume, and for this lecture, we will assume it is 1 all the time. Then the closed loop error becomes 1 over 1 plus G of 0. G of 0 being greater than 1 is actually suddenly a good thing, because the greater G of 0, the smaller the error. If G of 0 is 1, then the error is 1/2, which is less than 1. So in this case, with a closed loop system, we don't mind if we have a huge DC gain. It's actually a good thing, because we are reducing the error. Okay. But let's see how big that error is going to be depends on two things. Depends on the transfer function of the system, of the open loop system, and depends on the input. So we're going to establish that connection between the transfer function of the system and the input on one side and the steady state error on the other side. So we will start with the transfer function of the open loop system, and we will assume the most general case, this time written in the non-dimensional form. So you have a polynomial in the denominator, polynomial in the numerator. Denominator has this factor here, s to the power of L, where L is called type. So it determines the type of the system. So if there is no s, that means you have type 0, s to the power of 0, which is 1. Okay. So that is the type. K is just a steady state gain. Okay, now our closed loop system, remember it is limit s approaching 0 of s times r over 1 plus g, assuming h to be equal to 1. Let's cover now a few cases. So let's start with a type 0 system and a unit step input. And so let's see what the steady state error we are going to have. So steady state error equals to limit s approaching 0 of s times r is 1 over s. G, we are taking the general case here, but type 0 means there is no s here. That's type 0. So you simply have 1 times 0 plus 0 plus 0, and eventually you'll have 1. That's this one here. S is 0, S is 0. Up here as well, everything is 0, apart from 1 and apart from k, obviously. So here we have k times 1, we have 1 times 1 here. So when you solve the s here and 1 on s will cancel each other, so we have 1 over 1 plus k. Right. Let's leave this case for a while. So we have a constant steady state error. It's not 0, unfortunately, but it's not infinity, which is also good. OK. Let's now try a type 2 system and a unit ramp input. Unit ramp input, you have 1 over s squared here. Type 2 means you have an s squared down here. When you find this limit, you will get a 0. So this combination gives you 0 steady state error, which is much better. Another case, type 1 system and an impulse input. Impulse, yeah, unit impulse for simplicity. So unit impulse will have 1 up here. Type 1 will have an S over here. And that, again, will give us a 0 steady state error. Now, we can keep going on and on like this, combining all sorts of types with all sorts of inputs. Instead, let's present a table like this. So here you have the system type from 0, 1, 2, 3 onwards. Here you have different inputs: impulse, step, ramp, acceleration. Unit impulse, unit step, unit ramp, unit acceleration. And then you will see that you have a diagonal splitting 0 values and infinity values. The diagonal has a constant value. It's 1 over k pretty much all the way apart from here, 1 over 1 plus k. So the conclusion we can draw is that the increase in type will reduce the steady state error. The higher the type of the system, the more accurate the steady state performance. But remember what type means. It means integration. 1 over s means integration. So the more integrations you have in your system, the less the steady state error you are going to have. On the other hand, here you have an increased dynamics of the input. Impulse being the least dynamic one. It's always 0 apart from a very short period when it jumps to constant value and then back to 0 again. Step is more dynamic because it is obviously an integral of impulse. Ramp is integral of step, and so on and so forth. Now, an increase in the input order or input dynamics will result in an increase in steady state error. So, as you can see, impulses are good. They don't result in steady state errors at all. But steps, be careful. You would like at least one integration in the system to have a steady state error at 0. OK. Let's do a few more examples. So case 4, now we'll take a particular system. Instead of having those nth order and mth order polynomials, we are going to have real systems. So k over bs plus 1. So let's see, case 4. First of all, if the open loop transfer function is k over bs plus 1, let's find the closed loop transfer function. Closed loop, it will be g1 over 1 plus g1, because here we have 1. Sorry, minus is missing here. So this is a negative feedback loop. So it's probably this minus here. Just need to move it over here. Okay. So somehow the minus dropped out of this drawing. OK, so the closed loop transfer function is now k over bs plus 1 plus k. So it is still a first order system. And let's apply a ramp input. Applying a ramp input gives us the output, which is equal to inverse Laplace of 1 over s squared times the transfer function of the closed loop system. This solution can be found in the tables. Actually, let's do it. S squared s plus a, which is this one here. where A is 1 plus k. So we are going to have 1 over a squared times at minus 1 minus e to the minus at. So you have a sum of an exponential, which is transient, and you have a straight line, at minus 1 times some factor here. Okay? So this is what we are going to get. This is the exponential part, and this is the straight line part, or asymptote, or steady state part of the response. Okay, so this is our input, a unit ramp, 45 degrees. This is the output. This is the asymptote. Okay, so this is the asymptote. Our real output starts from 0 and then slowly approaches the asymptote. The error is the difference between the input and the output. So you start from 0, and then as the time progresses, you have more and more error. And this error keeps growing even when you reach the steady state case, because these two lines are not parallel. The input ramp and the output asymptote keep diverging. So at infinity, you will have an infinity error. So the steady state error is infinity. And if we wanted to check in our table, what is the type of this system? No, 0. It's the first order, but 0 type, because there is no s outside the brackets. Remember, type is s to the power L. L is the type. So this is a type 0 system and ramp input. So type 0, ramp input, that's infinity. So the steady state error is infinity. Case 1, so let's take a new system. This one is type 1 because it has s to the power 1 as a factor multiplying the polynomial. It is the second order system because once you expand this denominator, you get s squared. So it's a second order, but type 1. And let's apply a ramp again. Okay? But instead of checking the table, let's do the, again, time domain analysis. Closed loop system is g over 1 plus g. Closed loop transfer function, which is this one here. Input is a ramp function. So the output, it would be equal to the inverse Laplace transform of this expression here. For this, we will need partial fractions because there is nothing here that resembles our particular function. When you complete the partial fractions, you get the output like this. So you get two exponential terms, and that is the transient part, and then you have this straight line, or asymptote, or the steady state part of the response. However, what is important here is that the slope of the asymptote is the same as the slope of the input. It's a, yeah? Sorry? Because we said we started from this and then found the closed loop transfer function as g over 1 plus g. Okay. So here, this transient part, ignore it for a while. The steady state part is a straight line, 45-degree slope, offset by this alpha plus beta or alpha beta, a constant value. So this is the asymptote. When you include the transient part, this is the actual output. But remember, the input is a unit ramp which means parallel with the asymptote. So now the input ramp and the asymptote, they are parallel. So initially, the error will be growing from 0, but reach some constant value eventually. Because at infinity, these two lines are parallel, so you have a constant steady-state error. What that constant is, well, we can check up here. So type 1 ramp input, type 1 ramp input. So it's actually 1 over k, where k is the steady-state gain of the system. Okay. Now a few questions and answers. Okay. What sort of steady-state error does an integrator produce when driven by an impulse, step, ramp, acceleration? So what is the type of an integrator? It is 1, because you have an s down here, s to the power 1. The fact that you don't have anything else doesn't change that fact, that this is a type 1 system. So what you can do, either use the table or use the expression for the steady-state error. By the way, this equation will be given in your final exam. Again, not something you should worry very much about. Okay? So, type 1, impulse, step, ramp, acceleration. Type 1, impulse and step will give us 0 steady-state error. Ramp will give us a constant steady-state error, and acceleration will give us an infinity steady-state error. Okay, question 2. What is the closed-loop steady-state error of a system whose open-loop transfer function is, now you have real numbers here, 500 over s plus 9, s plus 5. Now, from what I can see here, this s should be actually lowercase s to avoid any confusion. So it's small s. And driven by step of height 10. So let's see how a non-unit input changes the steady-state error. So far, we always had a unit step, unit ramp, or unit impulse, unit acceleration, anything. Okay, so the closed-loop steady-state error is given by this equation, s times r over 1 plus g. S is still here. R is now 10 over s. 1 plus g, that would be the open loop transfer function. So when this s cancels this s down here, and this s is 0, and this s is 0, you have 9 times 5 is 45, so you have 10 times 45. Down here, you have 45 plus 500. So you have a steady-state error which is constant and which is slightly less than 1. Or if you use the tables, be careful. You have to multiply the steady-state error by the magnitude of the input, which is 10. So if you use the tables, okay, it is a type 0 system, and you have a step. So back in the tables, type 0 step input will give us 1 over 1 plus k. But times 10, because it is not a unit step, it is a step of magnitude 10. Okay. So 10 times 1 over 1 plus k, and we are getting the same. So sorry, and k is, yeah, what is k? K is 5 over 9 times 5. That is the DC gain, steady-state gain. So now 10 plus 1 over 1 plus 500 over 45 will give us the same value as here. Right, so this is the lecture on steady-state errors. You are going to have a small part of your final exam asking you to find a steady-state error or something. It shouldn't be too complicated. It's much more important thing is to understand the meaning, the relevance of steady-state errors. That what we said earlier, by applying a negative feedback loop, we improve the performance of the system. It is true, but there is always potential problems, that there could be a steady-state error present in the system. We improve the stability, not only performance. We very often improve the stability. Okay. Any questions or comments? Okay, I'm not really planning to do much on lecture 11, but just a very quick introduction. Actually, the last sentence I said was actually a very good introduction. I didn't think about it, to lecture 11. When you apply a negative feedback loop, you're hoping to improve the stability of the system. That means that your original transfer function, in this case P of S, may contain some poles that are not negative. They are positive. So contributing to instability of the system. Applying a negative feedback loop, most of the time, we will be able to push those positive poles into negative half of the S-plane to make our system stable. But whether we can do it or not will depend on this value k here. Oops. The value of k. So this lecture, lecture 11, called root locus technique, shows you how the value of k, when you vary k from 0 to infinity, how the poles move through the S-plane, how the roots of the denominator move through the S-plane. Why do we care? Because the poles tell us how stable the system is. Once again, if all poles are on the left-hand side of the S-plane, so either they are real and negative, or if they are complex, then real parts are negative, then the system is stable. So the system needs all roots of the denominator, called poles, to be on the left-hand side. If at least one pole is on the right-hand side, this system is unstable. So we are hoping that this negative feedback loop will push all our poles to the left-hand half of the S-plane. But what if they don't? Then that's why we need at least one parameter that we can play with, in this case k, to make sure that those poles will be there, will be where we want. Sometimes it's not only stability we are interested in. Sometimes we don't want any oscillations to happen. We want the system to be critically damped or overdamped. That means we want real poles, not complex conjugate. That can also be achieved by varying the value of k. But there are so many different cases, and we are going to establish some rules, again, next week, next Tuesday. We'll try to establish some rules of how the value of k dictates the stability of the closed-loop system, of the new system. OK. That's, I think, where we should stop for today. So on Tuesday, we have this lecture 11, which should conclude at least my part of the course. I still owe you laboratories. And just when we thought that we'll have the rig set up, now they move the rig because there is something more important than linear systems. How can anything be more important than linear systems is beyond me. So most likely we'll start our labs after the mid-semester break. Just watch the Moodle, watch the announcements, and the information will be there. OK, any questions or comments? Don't run away. Now our demonstrators will come in 10 minutes, so you can ask questions.
So sorry.
No, nothing worked.
It didn't work.
Well, at least they will have echo.
Sorry?
They have echo. They have the backup version.
I'm
Yeah.
not too sure because apparently they use that one to upload to Apple, I think.
Okay.
Yeah, so I don't think there's any recording. Someone did something with the microphone. Probably the previous recording guy.
Or maybe. Oh, you mean
Yeah,
this one?
Yeah,
Okay.
someone did something, and we're not sure what. They
Well,
changed.
anyway,
Yeah, I'm not sure if there'll be a recording.
I did my bit.
We did our best too.
250 students. Yeah, thanks.
did our best.
I know. Thanks. Oh yeah. No, that's okay, but I think don't worry, because it depends on if your initial error simplifies the system too much, then effectively you have an easier task than the person next to you. So in that case, you may not get full mark for the question. You mean the question two? No, that apart from the error in the block diagram, I don't know how serious the error was, so you will lose some time there. But the rest should be okay. The problem is if you get, for example, first order, then you're actually making easier job for you, and we don't want to encourage that. So, but it should be okay.
So this is, you said that's like the transfer function.
There's a transfer function.
Okay, but like you could also say that's like this function. Just that.
I would say it's S. Oh, well, depends on, no, it's S, not number. Yeah, I mean, unless you say, if I make a displacement, what kind of force am I going to get? In that case, it's easy. So if you reverse, if you say, displacement input and force input output, then yeah.
Is there a way to like
So Dancer is the visual is an integrator. Yeah, okay. I had one example somewhere back in, I think, lecture 5. The very end of it. Oh, yes. This is an integrator. This servo mechanism is an integrator. Because when we derive the transfer function, we got this. Okay, so everything is constant apart from that. So this is an integrator, but you have an electronic circuit that acts as an integrator. They are much smaller.
it's just hard to visualize like
Yeah.
you apply like a ramp but like it gets worse and worse if you apply a
No, but it's not. So if we agree that this is integrated, now you need a feedback loop. You need to measure this displacement and adjust the displacement of this lever. That would be a kind of feedback loop. And then you apply a ramp. Then you are pushing continuously without stopping. So we are talking about steady-state error over closed loop system. So it's not just error of this, but you have this inside the negative feedback loop.
so what would that negative feedback look like in real life?
It's usually so you have a sensor measuring this and an electrical signal, generating a force on this lever.
So it's not something
You can have mechanical feedback loops as well, but most time you apply you use sensors.
just really have a feedback of this.
No, maybe you draw a little sensor there and a cable, and then an electromagnetic motor or something like that.
This is a question about electricity. I think I
only or don't lose all. Depends on how well you did with the wrong transfer. So you got the wrong event. I mean, first of all, if you did the block diagram, this was fine. That's what you did.
And I show how I try to simplify.
Yeah. So what is your final transfer function?
X plus 4. S plus 4 on 2 S plus 2. Because I forgot to eliminate like as possible.
I'm instructing, I mean, I have two principles, obviously, one to prefer to marking language, to go for knowledge. I mean, if everything is right, no problem, it's full mark. But if not everything is right, then ask yourself, what does it mean now? So if you still know what to do with this, you'll get some mark. I can't really promise you get full mark of each.
Yeah, of course, yeah.
Okay. So, yeah, we have to wait and see. So you won't get zero. PT did it right. Okay, PT did it right.
And when do you expect to get
The course outline says 2 weeks. I don't want, if I rush it too much, I will have a lot of mistakes. A lot of mistakes. So there's no point rushing it too much. They should have their own pace. I call them during the meeting. I mean, otherwise it's Thursday. It's really 1 week. It's not your big one.
So where could be at the first start? Let me say the
Or the lecture or the
yeah,
course?
the lecture.
Okay.
We say that the error is actually R minus C, which is the difference between input and output.
Yes.
Right? If we do assumption that our error equals 0, that means input is exactly the same as output.
That's right.
Then why do we need the system?
The system provides, okay, you need a system, you need a system because you want 20 degrees. Otherwise it will be 40. You need a car because you need to move from here to wherever you won't need a transport. So the system is there. And now the question is how you get from your system what you want. Okay. So when I press this button, how do I get 20 degrees? So that's why we are talking about error. Because error, if we are getting 25 degrees, we still have a system. Still have a system that works. But it is not active. It has an error. So here we are analyzing errors. But again, actually this is a good example because we have temperature sensors here. So it is a closed loop system. So at 120, the system is giving us 25, but the sensor keeps checking that temperature and trying to create this error signal to reduce the temperature. But if the system is of such a type that it never gets the steady state error to 0, well, yeah, we need to know that.
Right here, so E0 infinity equals
It's not 0, it's open loop. Open loop closed loop.
yeah, okay. So I can't see the input here.
It's 1 over S. 1 over, R is 1 over,
Where is R?
it's 1 over S. That's the input. R is the input. And we said unit step input. So R is unit step.
Okay. And this one?
We actually not having much luck recently. Last class was interrupted by, you were not here on Tuesday. We have to leave the theater because we had the evacuation drill. And now we have this failure as well.
Yeah.
See, it's worth coming here, guys. You never know what will happen. Yeah.
So this is again, is that kind of linear system?
Oh, it's very non-linear. You can try to linearize it and derive transfer function that is actually very non-linear. But it is a feedback loop system. It is a negative because it has this sensor that actually controls the valve here. So if you're getting higher temperature, it actually reduces the intake of hot air. If the temperature is low, it increases the intake of hot air. So it is an example of a negative feedback loop system or control system.
Okay.
But linearity is really questionable. We can. Well, that will be an interesting exercise to create a linear model of a bootstrap system. That could be interesting.
So
I
we
actually have a thesis student working. She's simulating this system not this system, the whole cabin environment in the MATLAB. But that's different.
So saying that we could divide this into the linear system like that.
Yeah, this G has the compressor, heat exchanger, and turbine. And whatever else happens on the way to the cabin. H is the transfer function of the sensor, temperature sensor.
Alright. So these boxes are actually the transfer functions.
Well, you can try to derive transfer functions, but you have to make them linear. So you need differential equations, and you need linear differential equations, and then you can make transfer functions. I already see you doing this. you're already preparing yourself to do it.
Not really. So for this course, we're actually not doing this non-linear system.
No. That was the very first lecture I explained. We do linear, time invariant, deterministic system, continuous.
But most of the systems in the world are non-linear.
That's right, but some of them are linear enough. You remember linearization. If you pick an operating point, and then if your system doesn't deviate too much from the operating point, then you can assume it is linear.
So if I was doing this case, I'm supposed to linearize each of the boxes.
That's right.
Then put them into
Correct.
boxes.
Correct.
Oh, okay.
Correct.
Right. Thank you.
No problem. You're not going to be very busy. I expected that, but not really this much. I already have some. I just need to get, I will have to, email you both, so you can tell him what you've done this week and next week, so he can do it next week. No, I think what we can do very easily is just use, so you are losing 2 hours. So, instead of 15 for preparing the rig, you can claim 13. How about that? All from your mark. Marking is even easier because you claim it separately. You'll be paid for these 15 already. So let's not touch that. By mark, instead of 30, you claim 28. And he will claim 2 additional. No, I don't want anyone to work for free. No, yeah. Unfortunately, you don't. So yeah, they actually asked me about, I had to set another form because we are losing classes on Friday, but also in weekday on Tuesday. Tuesday is a public holiday as well. That's the day. Weekday, yeah. So you guys, you're losing some. And they asked me to provide quiz, losing how many hours. So guys, find less money next check. I couldn't, I had to try that information. Okay, that means semester break. next week I'll try to prepare, the sheet with the experiment. And the assignment I'll send to you. If you have time to read, good. If you don't, because you're on holiday, you don't have to do it. Then we'll talk when you come. So that will be Tuesday the 18th.
Monday I will be
Yeah, but Monday is a holiday.
Monday is a holiday and Monday I will be available.
Okay. Let me know. So just let me know. When you come back, let me know. And but I really hope by that time I'll have everything ready. So we can start. Apart from what they are doing in that teaching lab, they put something else and they moved over. Yeah. So doesn't mean we can't. I also have to sit down with Bruce to get the timetable before I let them enroll. But that's not your problem. That's
The problem is like week 8 and week 9.
yeah, both to start with week 8. So during the break, we have everything sorted out. You can start with week 8. Otherwise, we can't.
You know something with the teaching wind tunnel yet, or?
It's still sitting. Every time I walk there, I check. It's still there. It's light blue, so you can't miss it. Apparently, Danielle is running some experiments. They want to remove the open loop.
Yeah, the open jet wind tunnel. They want to get rid of it, but
Yes, but she's still doing some experiments. That's
no.
what I thought.
Oh, but yours isn't on there.
Sorry,
Who told you that?
Nancy. Well, I don't know. She doesn't have to know about the research.
No, I know, but I think it's just like we could put it in any time. It's just
Okay.
I think it's just the people that do want to move it are just being yeah. Because the open jet wind tunnel is you know where the anechoic chamber is now?
No, I haven't been there
Oh, you haven't been.
for a year since you did your experiment last year.
Oh, okay. Well, yeah, nothing's changed. It's all the same, but we're putting your tunnel or the teaching one behind the supersonic one. All this stage.
Yeah,
So,
but they are not doing it.
no. Yeah, we were thinking about maybe using it in the aerodynamic course as well. Maybe getting them to do some like airfoil design and then get them 3D printed and then test it.
Yeah, I mean, I was hoping, this is a pretty expensive piece of equipment, and I was hoping it would be used for
Oh yeah.
not only for one experiment in the year. I was also thinking, but now the 4D design is changing. That maybe something can be done in that wind tunnel instead of a big one.
Yeah.
I don't know about that, but at least that was one of the ideas.
Yeah. Well, the aerodynamic course, I'm always love to use it. Like,
Yeah, okay, so that's good. Yeah, thanks. I mean, there's little I can do. If they can't move it, I'll have to approach Convenance to use that big wind tunnel once again.
yeah, we'll have to. Oh.
No, I mean, every time I think they won't happen. Yeah, but that's pretty much all it is.
So when should I be due?
30th May.
Okay, so that's close. Is this the first one?
Yeah. I'll be going back to India like my first. We went to India in December, so and she stayed there. So we have family and all. It's easier over there rather than in New York.
Fair enough.
So I'll be going back in week 3rd at the end of week 12.
Okay. All done on that, I would say. Playing separately for it. That spreadsheet that he sent after the first test. Oh, you did. Yeah, if you send that plain form, you fill in the spreadsheet, send it up to her, and you say, oh, Mark, this is take this many hours per month. Or any extra hours, supervising one. Are you writing that
laboratory. I think that's for laboratory.
But do you put it in contact with if you want to go, like, you've got marketing, we don't, well, I don't, so I'm going to say, but it's you.
No, yeah, sure.
One question. You don't want them to see it.
I wouldn't do it today. Maybe I'll do it around the weekend.
Which one are you asking?
Question 2.
You're going to have so much fun. Got that,
Yeah.
that junction wrong. Yeah, it all gets so confusing. It was like, one of my friends was going to take it, and I was like, oh yeah, like, I said here and I multiplied by 1 on x instead of dividing by 1 on x, and I was just like, no 1 on x is still everywhere. Yeah, well, oh, you have your yeah. Oh, okay.
Zora already said that if you want to tell me. We are marking the reach. There are hardly any students here. Maybe we'll go right inside.
You go, and then you can
Yeah, I
take
don't
this
know.
with you.
Yeah.
This is white.
Oh, okay.
It was wrongly part.
Like it wasn't like it's like 90% of the aesthetic dates.
No, no, yeah,
Oh, yeah. Wait, like nobody set up a lecture.
The quark section has solution and questions, the same shit.
guys are also
you wanted it to be small. So the widest part of the white bag, you think it's like prestige. It takes way too much time. Like, you think it's good because you're getting paid for it, but it's a lot of time. That's true. How many things if you drink 3 cups? Yeah. Yeah, I know. I had to pay all my car stuff off this week, and it was just like money in, money out. It's like not like zero savings.
It means your system reaches stable.
It is a steady state solution.
Steady state.
Impulse input. You do impulses at 1 month intervals.
I've been hosting Arrow 3 There is. It's optional. I don't know why I signed up for it, but I'm doing it.
I haven't heard about it. It's probably naive.
Pardon?
It's probably naive. The older student. Sorry, I didn't know it.
Actually, I think I
Yeah.
I remember yesterday I think I spoke to you about
Yep.
it turns out I think I didn't do any part of it.
It was like one of the jump tests.
Well, I mean, it was how I didn't realize that you had to make an entire, you had to find the bottom part and get rid of one half. That makes so much sense. Did anyone else ask about that, or am I the only one?
I've noticed a lot of people screwed up. Even people were moving the junction, but getting the movement of the junction wrong because they thought they were moving over one of the integrals. So, like, I'd say out of the papers that I did look at, which were probably 10 to 20, I'd say 30% of them were not doing the right thing.
30%.
I'd say 30% were not doing the right thing. Like, at the start, like, I don't know about the other question, but just getting that transfer function.
Once you get the transfer function wrong, the rest of the questions are even, because then
So there might have been more that were screwing up later on, but there were about 30% of people that were struggling to get that block diagram
times
junction
the
coming
output.
back is to move that junction to the half
Because
behind the fork.
yeah, because the 2 times output's still nested.
Yeah, exactly.
Well, I get anyone to do it. Or am I getting everything wrong?
I don't know who's marking it, so I wouldn't know. It's none of the things. Sorry. You would have got question 1 out there.
I thought so.
Did you go to the room lecture?
Yeah. I did, and then I realized that, well, I said that it was amplified, but I said it was VS, but it should have been UXA.
I can't remember the question.
VI should not have had an amplifier at the front. It should have been multiplying by the load curve rather than the amplifier.
Oh, okay. Yeah.
And so I got that wrong, and I didn't have time to go back because it's
It would have just been one constant.
no, it would have been a constant in the wrong position, which means that you get X the step in.
But so your magnitude would have been off by
By okay,
yeah. It's just one constant. Like most of it would have been.
yeah, everything else
You'd have had all your
for that one constant.
yeah. You would have had the first order system, the second order system, but you were just running one constant. It happens. I don't find it.
Sorry, I'm just. What? I mean, it's nothing.
No, it's okay. Just have to wait.
I think I already know.
You don't look like. I don't know how they mark it. I don't know how much marks they pick up for carry-on errors. Zorin usually tries to be quite good in terms of like setting up the marking, but it's such that if there is a carry-on error, they actually do go through and compare. So even if you've got a constant in your yeah, but even though that they then should take into account the fact that in part B when you're calculating connection you did have, or you were doing the right methods for part B rather than, just not getting it correct. The methodology would be all this, but
well, I mean, I did that for like the second time question 2, and I did the whole expansion of the function. No, it comes out, I get a number, it's way too large, and then I might have gotten marks as that, but then I crossed it all out and did the M percentage thing. But it's probably not possible because it's just like you shove it down.
I can't remember the question, but yeah. Just wait for the results. If you need to, when you need to get your paper back, go and talk to Ryan about it. He's usually good. He'll sit down with you for a good like half hour if you really want, and he'll go through it with you. Oh yeah, you'll just have to wait for them.
The average was way higher than this one, like by quite some distance.
What was the average mark?
Four. I got like a 6.
I'm guessing the average would be quite similar.
I think the average would be higher.
Probably just. It'll probably be a pass.
Well, I mean,
50-55%, but it wouldn't be much more than that.
why? I thought they did the questions. They did the questions in revision.
Yeah, but how many people did actually went to the revision? And we were told to really like we were told to start working through, so most students wouldn't have touched question 10 or 2. So if they didn't go to the lecture, even if they went to the tutorials, they probably haven't seen it. A lot of people were looking up. Both
3D screen. Oh, you can't? Okay. No problem, no problem. You're fine. So I have this semester, I have 2 more. Yeah. I did. I did while I was in Yugoslavia. I worked for I don't really call it industry, because of still research, but it was not university. I didn't teach, and we've had a lot of collaboration. I worked for the army. Army battle simulation.
Oh, I thought you were in the army. On the battlefield.
On a simulated battlefield. Yeah, you have passion, mission, profession, vocation. Handy, passion and mission. Word mission doesn't you are barely paid for it. Oh, okay. Passion, profession. You are graded on the end, I guess.
The red dot in the middle?
Okay. Academic. Oh, send it.
I'll send it to you.
Do you have any work, any job?
You can't hear it at all though. You can't hear it at all. Everyone just talks. Yeah. I went to she teaches like a bit of the CFD stuff. And I went to those and like when you actually listen to her, she explains it pretty well. Like but just nobody listens. So I couldn't hear a thing. I was sitting like as close to the front as possible and you still couldn't hear it.